Whether you're hacking on Arduinos in your garage for fun or designing the next great smart gadget, adding a display to your embedded device adds to the ease of use and the professionalism of your project in a way that few things can. With just a glance, a screen can convey critical information to the user, and it presents an interface to make controlling the device straightforward. Making that display a touchscreen brings your project to a whole new level. Even the most complex devices can be controlled with just a few taps and swipes of the screen. And frankly, it's what consumers expect these days. But adding even a simple display to your Arduino, ESP32, Pico, or other microcontroller is quite a challenge. From choosing the right display, to wiring it up, to getting it talking to your microcontroller, to drawing shapes and text. There's just so much to learn. Now, there are hundreds and hundreds of tutorials for using various displays on various platforms, but what I found to be missing was a video that took a step back and just presented the basics. So that's what this video is. I'm not going to be talking about any one display or any one microcontroller, but instead I'll present the concepts of how displays work and how you can get a microcontroller to command one. Let's get into it. As mentioned, this video will present an introduction to displays, define the various concepts in lingo, and demonstrate how to use them with microcontrollers. I will lightly touch on a wide variety of topics, starting with how displays work, then the different types, then moving on to interfacing with microcontrollers. Next, we'll talk coding, buffers, color formats, and how to send the data to the display. Then onto drawing shapes, text, and images, and using input devices like touchscreens. I'll wrap up by discussing graphics libraries in general, and then introduce you to the one I use, LVGL. This video is not a tutorial. I won't be showing you how to hook up a display, and I show very minimal code. I believe that many tutorials are too procedural. Hook these wires up, type this in, and they fail to explain why you're doing it, what the effect of what you're doing is, and what are the other options. Tutorials also tend to focus on specific hardware, and they don't really give you the information you need to choose your hardware. My hope is that you'll take the information in this video and use it to research the approach and specific hardware that fits your application. You can then find all manner of tutorials specific to your hardware and software. It's important to have a basic understanding of how a display works. The majority of displays, regardless of the exact technology, are doing one of two things. They either block light or they produce light, selectively and at a pixel-by-pixel level. There are a lot of oddball displays, but for this video, we're talking about solid-state panel displays, like LCDs or OLEDs. These are two-dimensional arrays where each cell is a pixel, which can be independently controlled. The most common type of display is the liquid crystal display, LCD, which works by blocking light. Each pixel of an LCD screen contains a cell of microscopic crystals that change their optical properties based on applied voltage. This is usually a proportional effect, so it's not just on or off, but can vary its darkness depending on how hard it is driven. LCDs do not produce light, but instead rely on backlighting or a reflector to push light through them. LCDs are inherently monochrome. To make a color display, the manufacturer places a color filter array on top of the display, with each pixel made up of 3 cells, one each for the red, green, and blue channels. Light-producing displays, such as OLEDs and micro-LEDs, are more simple conceptually. Each pixel is essentially an individually controlled light bulb. Color displays are achieved by making each pixel out of 3 lights, again, red, green, and blue. And like LCDs, the brightness of each color of each pixel can be varied to produce millions of color combinations. What I've just described is how each pixel behaves, but another consideration is how the pixels are controlled, which is independent of the type of display. There are 2 main options: character displays and graphical displays. A large portion of what most people do with displays is show text, so character displays take advantage of this to make programming much easier. Rather than arranging the pixels in an equally spaced grid, character displays arrange them in blocks of pixels, often 5 by 8. Each block is intended to display a single character. You don't control what the actual pixels are doing in each block, Instead, you tell each block what character to be. Generally, the character mapping correlates to the ASCII characters, so you send it hex 5A for the letter Z, for instance. This allows you to just write strings in your code and send them over without modification. In contrast, graphical displays are two-dimensional grids of pixels where every pixel is independently controlled. You can turn on 0 pixels, or 1, or all but 1, or all of them, any combination. Because of this, you can show pretty much anything. Custom symbols, images, different fonts, even animations. All of this is possible on a graphical display. But the complexity goes way up compared to character displays, as you can't just send it a string. Take the uppercase character R, for instance. It's just 1 byte, hex 52 on a character display. On a graphical display, you need to figure out what each pixel should be. Perhaps something like this, which would be represented by this. Then you have to figure out where to put this character on the display and how exactly to get your display to do that. I'm going to talk a lot more about graphical displays, particularly color displays, but first I need to discuss interfaces and driver chips. We've established that display screens are arrays of pixels that either selectively produce or block light, but how do we actually control those pixels? Well, luckily, we don't have to worry about powering the LEDs, scanning across the array, or modulating voltages, because pretty much every display that you're going to encounter has an integrated driver chip. This driver chip sits between the display and your microcontroller, connecting through a parallel or serial bus. It also connects to every row and every column of the display, so these drivers can have hundreds and even thousands of pins. These driver chips remove much of the complexity of a display, and from our perspective, there's really only two things to concern ourselves with. The first is the communication interface between the display and the microcontroller. The two easiest options that most tinkerers are probably already familiar with are I2C and SPI. These are serial interfaces, so 1 bit at a time, with I2C generally being slower than SPI, but using less wires. Nearly every microcontroller has SPI and I2C peripherals, with some microcontrollers and displays also being capable of quad SPI, which has 4 data lines and 4 times the data throughput of traditional SPI. The next step up in terms of data throughput are parallel interfaces such as the 6800 and 8080 buses. These both offer up to 18 bidirectional data lines to write or read the data to the display, as well as control and timing signals, although it is common for only 8 or 16 of those signals to be used. Next, there are displays whose driver chips don't have memory built in, but they instead require a microcontroller to store the pixel data and refresh the display. This interface is called MIPI-DPI, and it consists of parallel data lines as well as horizontal and vertical sync signals. Lastly, there is the MIPI-DSI serial interface. This interface uses 1 to 4 low-voltage differential data lanes and a clock lane. These lanes can be fast, gigabits per second per lane. MIPI-DSI is quite complicated, but suffice it to say that it's generally found on higher resolution displays and higher-end microcontrollers. I'd probably advise beginners to stay away from either of these interfaces. They tend to be expensive, have tricky hardware considerations, and require additional coding. The driver chip in each display determines which of these interfaces you can use. Smaller displays, or displays with limited color depth, can get away with I2C or SPI and still refresh at a reasonable rate. If you pick a high-resolution display with 24-bit color, though, then you'll likely need a faster interface like MIPI-DSI. Make sure you consult the datasheet when buying a display to see what you're getting yourself into. The other feature of the driver chip that you need to be familiar with are the configuration registers. Driver chips are designed for a certain type and a maximum size of display, but can be used in displays with differing properties. Because of this, there are registers to set things like voltage levels, charging time, clocking options, and so forth. The display manufacturer usually specifies how to set these. Then there are options for things like flipping the display, setting the size of the display, and ordering which the pixels are addressed. On character displays, there can be multiple character tables and double-height fonts. And there can be graphical commands, things like clearing the screen or scrolling the display in a given direction. Some displays, like this one, even offer primitive shapes. This one can draw lines, rectangles, and copy regions from one spot to another, all on the display with minimal commands. This is driver chip specific, so I again recommend consulting the datasheet for your display to see what options are available. Once you're talking to the display and you've set the configuration registers, there's really only one thing to do: send pixel data. Which brings us to display programming. Now, this is a big topic, but I'm going to be discussing what I think are the most basic and universal ways to do it. But be cognizant there are exceptions to what I'm going to say. Programming a display really boils down to three things: figuring out what and where to draw on the display, receiving feedback from the display, such as buttons or a touchscreen, and sending new pixel data to the display. Let's touch on each of these. We know that a graphical display is merely an array of pixels, each one independently controlled. So it's obvious that we need some way to keep track of what each pixel should be. This is most commonly done with a frame buffer. A frame buffer is simply a data array in your code, usually the full size of the display, that holds each pixel's value. The rest of the graphics code modifies the contents of this buffer, drawing shapes or characters, for instance. When it is time to update the display, the buffer's contents are sent over the communication bus to the display controller. There are many variations of the frame buffer. Sometimes two frame buffers are used so that one can be modified while the other is sent to the display. To save RAM space, a partial frame buffer can also be used, whose size is a fraction of the display resolution. Speaking of memory size, let's talk briefly about the representation of color and its implications. Color displays support a certain number of bits per color, often 6 or 8 bits, meaning that a single pixel takes 18 or 24 bits to define. 6 bits per color is referred to as RGB 666, and 8 bits as RGB 888. In many applications, however, these color formats are non-ideal. They are large, and they can take up large portions of the memory. And on 32-bit systems, data is stored in 32-bit chunks, which neither of these fit nicely into. So engineers thought of other color formats, namely RGB 565, which represents red and blue with only 5 bits, making it around 16 bits per pixel. You can take this a step further with RGB 332, which is only 8 bits per pixel. There's also a lookup table approach called L8, where your frame buffer stores 8-bit values that correspond to RGB 888 or RGB 666 colors. And finally, monochrome displays can represent grays with up to 8 bits, but you'll often find it's just on or off, a single bit per pixel. There are a lot more color formats. Wikipedia has a whole page on them if you're bored. You're probably thinking, 24 bits per pixel is nothing. But remember, we're dealing with memory-constrained microcontrollers. As an example, this display is 160 by 128, or 20,480 pixels. At 24 bits per pixel, it needs about 500,000 bits, or 62 kilobytes. Let's look at some common microcontrollers. The Atmel ATmega 328P, which is used in the Arduino Uno R3, only has 2 kilobytes of RAM, nowhere near enough for just the frame buffer. The STM32 Blue Pill uses the STM32F103, which only has 20 kilobytes. Again, not enough. You need to get to a fairly powerful microcontroller, something like a mid-range Cortex M4 or so, to really get enough RAM to run this display without external memory. Speaking of that, if you're hoping to do anything complicated like double buffering or showing images, it's probably wise to add external RAM and flash, or find a development board that does that. If you're building your own hardware, you're going to need a circuit board to add that external RAM and flash to, and that's where the sponsor of this video comes in, JLC PCB. JLC PCB makes high-quality, affordable circuit boards with all the options and features to meet your needs. They offer boards from simple 2-layer designs all the way to 32 layers, as well as a variety of substrates including metal, flexible, and RF options like Rogers and Teflon. And if you're dreading soldering your boards, they also offer affordable PCB assembly. Their online quoting tool will load your design files and give you a quote in seconds. If you're building a board with a microcontroller and display, You'll likely want additional routing layers and controlled impedance, so JLC-PCB's 6-layer service is a great option. Advanced features like via in-pad are included, and they're running a special on 6-layer boards right now that makes them surprisingly affordable. There's a link in the description for these offers, and be sure to check out their other services while you're there. Once you've established a frame buffer, the next step is getting that data to the display. First, you generally need to tell the display that you're about to send it frame data. Sometimes this is done with a discrete input signal, other times there's a command sent over the interface, as is the case with this display. It is also sometimes necessary to set the starting point for the data. Basically, you're setting the pointer for the first pixel you want to fill, and the display will increment from there. Once the display is configured to receive the data, you need to start the microcontroller's serial or parallel peripheral to send the data. For color displays of even moderate resolution, it's important to do this without blocking the processor from doing other tasks. To explain why, let me go back to this display. As mentioned, this is 20,480 pixels, and I actually use 16-bit color RGB565. I'm running this display using SPI, which, according to the datasheet, can be clocked at up to 4 MHz. I want to refresh the display 30 times per second so that it appears smooth. Doing the math, I need to send almost 10 million bits per second. You can see the problem. With SPI at 4 MHz, I can't get more than 4 million bits per second, or around 12 frames per second. To solve this on this particular project, I actually just cranked the SPI bus speed up to around 11 MHz, which, despite being way faster than the datasheet recommends, actually works fine. Regardless, you can see why I can't transfer data in a way that blocks the processor, because the processor wouldn't have a chance to do anything else. The most optimal way to send data without locking up the processor is with the direct memory access, or DMA peripheral. This hardware is included on most microcontrollers, and it can autonomously move data from memory to the peripherals, or vice versa, all behind the scenes. The processor only intervenes periodically to re-trigger the transfer, giving it time to do other tasks like writing to the frame buffer. Setting up and using DMA is relatively straightforward. On the STM32F4 in this, it was just a few configuration lines and a single line to initiate the transfer. Then there's an optional callback function when the transfer completes. If you're not familiar with DMA, I encourage you to look for tutorials specific to your microcontroller. When using DMA to transfer the buffer, there's a chance that the processor will be writing to the frame buffer as the DMA is moving it out. This can lead to tearing, which is when a partially updated frame is displayed. This is the benefit to double buffering. The draw buffer is modified by the processor, while the other buffer is being sent out. When the sending and writing completes, simply copy the draw buffer to the other buffer and repeat. Whether you need this depends on how rapidly your display is changing and how long it takes to write and send the frame buffer out. That's basically it. Tell the display where to start, that you're sending data, and then initiate the transfer using a non-blocking method like DMA. But how do you fill the frame buffer in the first place, and with what? This is another huge topic that could fill a series of videos, so I'm going to just touch on the basics. General advice, primitive shapes, text, and bitmaps. First, when you're writing code to fill the frame buffer, you're going to want to break it into building blocks that can be individually drawn. Examples of these building blocks would be background fills, drawing shapes or buttons, adding text fields, and even complex things like animations, scrolling objects, keyboards, and so on. You then take these building blocks and you stack them to create the full user interface. This is easily done with opaque objects, like the color formats I previously discussed, and overwriting the frame buffer with a new object. This will place the new object on top of whatever is existing, effectively stacking the objects. Another common option is to use an alpha channel to describe the opacity of the color. The color format used for this is ARGB8888, with 8 bits each for alpha, red, green, and blue channels. To determine pixel color, you mix the object's ARGB value with the existing value. Displays can't show alpha, so before setting the pixel data, you need to do some math to convert to the appropriate RGB format. Now this can get quite complicated, so I'll leave you to research it if you're interested. Let's talk about drawing primitive shapes. Background fills and rectangles are very straightforward. Just loop through the desired region and fill it with the color. Other shapes like lines, arcs, circles, and ellipses can also be simple to draw because they can be mathematically defined and calculated. The problem is that displays have discrete, fixed pixel locations. Say you have this line, and your pixels are evenly spaced on a grid. You calculate your y value for each x location. Well, you find that the y value at x equals 8 is 55.6. There isn't a pixel at 55.6, so where do you put it? The simplest solution is just to round to the nearest pixel, which will produce a line that is aliased like this. Applying a simple anti-aliasing filter produces this result. You can also proportionally split between the adjacent pixels like this. Either way, you're going to want to interpolate using the alpha channel, or stacking will look weird. This simple example goes to show that even drawing a line is fairly difficult. Next up is text. If you're adding a display, you probably want to display text. And this isn't easy on a graphical display because microcontrollers don't have fonts built in. So it's up to you to tell it what an A or a B or a C looks like. The common way to do this is with bitmaps. For a given font size, where font size is generally measured as the height of the character in pixels, you determine what each character should look like, and then you save each character in memory. When you want to display that character, you copy the bitmap to the appropriate location on the screen. This is simple if you make each character the same width and height, and you equally space them, like a character display would do, for instance. But good-looking text has characters that go above and below the line of text, and you'll also want to adjust the spacing between letters, which is called the kerning. These are tremendously complicated topics that I'm not going to get into, but suffice it to say that implementing this from scratch would be quite an undertaking. One more thing to note, you don't have to draw out and code up character set bitmaps by hand. There are tools you can use to take a font from your computer and do it for you, and there are also pre-compiled fonts. I've linked a few in the description. As with text, the easiest way to display images is to save uncompressed bitmaps in memory and to move them to the display when you need them. Again, there are online tools that can create these bitmaps. Most photo editors can as well. But the size of these files can really add up. Remember when I mentioned how large a single display buffer can be? You need the same amount of memory for each full-size bitmap. This might not be an issue with external flash or only a few images, but compressed image formats like JPEG were invented to solve this problem. Some high-end microcontrollers have hardware JPEG decoding, so look into those if you think you'll be doing a lot of image work. Displays feed information to the user, but generally the user also needs to provide inputs to the microcontroller. This is often done with tactile controls, buttons and encoders, or a touchscreen. Integrating tactile input devices with a display is conceptually simple. Most commonly, you have up and down signals from buttons or the encoder, and an OK button, or clicking the encoder knob. The way I do this is to have a variable keep track of my position on the screen, changing it in response to the up and down signals. When OK is pressed, simply call the appropriate function based on the current cursor location. A caret or highlighting a line works great to indicate your location. Encoders and buttons are also great for changing values on screen, say to input a number. For all these cases, you'll need logic in the background that updates the display based on your inputs. Touchscreens and their benefits need little discussion. I mean, there's a fair chance you're watching this on a touchscreen device. Implementing a touchscreen can be tricky though. Touch digitizers usually report the XY coordinate of touch with a certain number of bits, and you'll likely want to scale that to match the size of your display. For example, if the touchscreen reports touches with 8-bit resolution, so 0 to 255, in both the X and Y directions, scaling that to match the size of your display, say 240 by 320, will allow one-to-one mapping of the touch location to the appropriate pixel. Clicking on-screen objects with a touchscreen is fairly straightforward. You keep track of where you've drawn objects, and then when a touch registers, you check and see if the X and Y coordinates fall where you know an object is. And if so, you trigger the appropriate action. Anything beyond this can get quite complicated. Things like the strength of the touch, how long it goes on, did a pinch or a gesture occur? Then there's multi-touch, where you might have 5 or 10 separate points. Suffice it to say that implementing a touchscreen at a low level can be straightforward, but it can quickly get out of hand. If all this seems too complicated, then I've got good news. Everything I've just discussed, far more actually, has already been written and packaged into various libraries. Simply download them, link them in your project, and you can get started developing a GUI in minutes rather than weeks. There are tons of graphical development tools for microcontrollers, but there are some distinctions between them. First, there are code-based libraries, and then there are drag and drop type softwares, where you arrange the elements and it writes the code for you. Next, many manufacturers offer free graphics tools, but they are often locked to that vendor's chips. On the flip side, commercial and open source packages are usually portable between any suitable microcontroller. Speaking of open source, cost and licensing is a big deal. Some packages are open source, some are closed but free, and some require paid licenses, some very expensive. Examples of graphical development tools are the free and open source libraries like LVGL. There's GUI development software like Embedded Wizard, which ranges from free to moderately expensive depending on your needs. There's TouchGFX, which is free from STMicro, but only for STM32 chips. And then there are full-blown commercial solutions like Qt, with proportionally full-blown price tags. Which of these makes sense for you depends on what you're doing. I initially started with TouchGFX, but ultimately I wanted the portability and an open source code base, so I pivoted to LVGL. These tools have a lot in common. The biggest thing they do is fill the frame buffer. What they fill it with and how they do that can vary widely, but common things are text boxes, buttons, menus, images, and widgets like sliders or gauges. These tools handle dynamic updating of the display, such as changing text in response to an input, repeatedly updating images to form an animation, or just refreshing buttons and lists in response to presses or slider movement. The libraries generally have some mechanism for periodically sending the frame buffer to the display. The implementation can vary, but it's common to update the display on a timer. There may also be a flag that lets you know when the library has finished its drawing, and that way you can synchronize updating the screen with the library. The other primary thing these graphics libraries do is provide a mechanism for user interaction with the interface. If you're adding buttons, sliders, or scrollable lists, or whatever, you need some way to manipulate those. The libraries have functionality to tie the movement of an encoder wheel, physical buttons or touchscreens, even mice and keyboards, to movements on the display, and actions such as switching screens or triggering blocks of code. You will generally need to write a small amount of code custom to your hardware to tie the button, touchscreen, or encoder signals to the graphics library, but then the library will take care of the rest. And unless you're using a tool with a pre-made configuration for your exact hardware, the graphics libraries aren't going to handle configuring or sending the data to the display. You're going to need to find or write the drivers to initialize the communication interface, configure the display, and handle sending out the frame buffer. Now for a very brief introduction into LVGL, the Light and Versatile Graphics Library. LVGL is a free and open source microcontroller graphics library. It's designed to create interfaces that feel natural and emulate what we've come to expect from touchscreen devices. I personally chose LVGL because it's open source, portable to any suitable microcontroller, it is widely used and supported with an active forum, it has a handy PC simulator, and it's code-based, which I find easier to understand and modify. If you want a drag-and-drop graphical tool, there are options that essentially write LVGL code for you. Squareline Studio has historically been the popular choice, and perhaps it still is, but it seems that there was a parting of ways between the LVGL and Squareline developers. There's a new option though, as LVGL released their UI editor a couple of weeks ago. I haven't had a chance to use this yet, but if you have, let me know in the comments what you thought. LVGL has a hierarchical structure, with the top being the display. Each LVGL display maps to a physical piece of hardware, so if you have one physical LCD, then you have one display in LVGL. Just below this are screens, which are the base of the tree on which you're going to stack elements, or widgets as LVGL calls them. There are dozens of widgets, including labels, buttons, message boxes, menus, tables, and so forth. Once you've created one or more screens, you add widgets to them, and then you can add widgets to those widgets, and so on, in a parent-child structure. The properties of the parent generally pass to the child, unless it's overridden. Events are used in LVGL to interact with widgets. Events can be triggered by a wide variety of things, but a common one is pressing a button. This triggers a callback function where you can perform pretty much any action. LVGL also includes functionality to control how the various widgets appear. First, there's the concept of states. Widgets can take on states depending on what is happening to them. For instance, there's the default state, there's the state when it's pressed, and so on. You can change the appearance of a widget overall or in response to a state by using styles. Styles are objects that contain things like background color, the border width, the text size and color, and so forth. Getting LVGL running on your hardware takes just a couple of steps. You of course need to download and link the files. Then there's a configuration file which allows you to change various options, font sizes, which widgets to build. I would guess that there are over 100 customizable settings in there. Next, you need to periodically tell LVGL what time it is, and you do this with the LVTick_set callback function, which is just a line or two on most microcontrollers. Next, you need to create your display by establishing the size, color format, creating frame buffers, and importantly, writing the flush callback function, which purpose is to send the frame buffer to the physical display. Finally, you need to set up your input devices, be it buttons, an encoder, or a touchscreen. There's a lot more to LVGL, too much to get into here, but suffice it to say that it supports things like different fonts, displaying images and animations, file systems, and real-time operating systems. There's an excellent PC simulator that allows development without a microcontroller and display in front of you. The documentation and examples on LVGL's website are quite thorough, and there are hundreds of tutorials on using the library. It is easy to get started with. You can basically install it, run the provided examples, and get started dissecting those examples in a matter of minutes. At the same time, it's a very extensive library with tons of options, and I personally do not pretend to have mastered it. I used LVGL in my programming fixture build with great success, but I will say that it's not perfect. For instance, I found some underdocumented issues regarding rotary encoders in certain widgets, but I think that the performance and cost is really hard to beat. One last thing, if you're looking to dip your toes into microcontroller display development, or you're just doing a one-off project, I highly recommend finding a development board with the features you're looking for, like external RAM and flash. If you buy a development board from a reputable company, you can be fairly assured that the hardware works well together and the drivers are probably already written and available for download. And you can't build this for what they charge. Take this STM32 F469 Discovery board, for instance. This is like $65. Just the microcontroller is $18. Then I need the PCB, the display, the memory, the connectors. It'd cost me $200 to build this, easily. So unless you really need some specific custom parts, I think you're better off just buying an eval board. I hope this video has given enough information for you to decide if you want to tackle adding a display to your next project, and whether you'll keep it simple with a character display, explore a monochrome graphical display, or go all the way to full color. Once you've decided, do some research. Look for the exact hardware you're going to use, and see if there is pre-existing code that works with the display's driver chip. Familiarize yourself with the datasheets, and look for tutorials specific to your hardware, which you can almost certainly find on YouTube or some other corner of the internet. And then have fun, because I personally think that GUI development is one of the most satisfying things you can do with a microcontroller. That's all I've got today. Be sure to like and subscribe if you found this interesting or useful. And as always, if you have any questions, concerns, anecdotes, or if I've made any glaring mistakes or omissions, feel free to drop a comment below, and I'll do my best to respond. Thanks for watching.